So, section 1.5, operation on functions. And if you just glance down here at 1, 2, 3, 4, we've got a whole lot of function notation here. And over to the right, you see some things about domain. Okay, and in line 1, basically what's happening is we've got a function f and g, and we're going to add them together. Okay, and we see notation. If we take f and we subtract g, then we can write it this way: f minus g of x, or f times g of x. How would we construct that? Well, we'd simply take the f of x, the output, and multiply it times the g of x output. Okay. So, in other words, we can add functions, subtract functions, and multiply functions to create other functions. Okay, it sort of stems back to if we take a real number and we add, subtract, or multiply that real number by another one, then we'll just simply get a real number back. Okay. Now off to the side, you can see that for addition, subtraction, and multiplication of two functions, then to find the domain of that, we simply take the intersection of the domain of the original two functions. Okay, now the fourth one has a slightly different explanation for the domain. But here we have f divided by g of x, and we're simply dividing f by g of x. Okay, but now since we're dividing, we cannot have g of x equal to 0, because in that case we either get 1 divided by 0 or we get 0 divided by 0, and neither one of these are real numbers. 1 divided by 0 is undefined, 0 divided by 0 is indeterminate, and we don't necessarily have to have 1 on the top. We could have any other number. We could have 2, 3, 4, or a negative number, but if we just simply have some number other than 0 divided by 0, we get an undefined output. If you put that in your calculator, say 1 divided by 0, it'll probably return an error. So now for dividing two functions, we say that the domain of that particular function would be the intersection of the original two, with the exception that whichever one is contained in the denominator, that one cannot be 0. Okay, so example 1, we're going to calculate this new function, and this is telling us that it's composed by adding f and g together, and whatever that is, we put 2 in it. Okay, we don't have to know exactly what that function is. We can just simply calculate instead f of 2 and g of 2 and add those two outputs. Okay. So what do we get if we put 2 into f of x? We have 3 times 2. Oh. Let me erase this. Okay. We have 3 times 2 minus 1. Which is, well, that's just the f of x part. Let me erase this -6. Okay, so this is f of 2. I'll put that in brackets. So we have f of 2, and then we're adding to it g of 2. G is x squared minus 2x, and so I put 2 in the place of x, and then I subtract 2 multiplied by 2. And this set of brackets would be g of 2. 3 times 2 is 6 minus 1. 2 squared is 4, and then minus 4. 2 times 2 with a minus. And now we just simply have 6 minus 1 in the first set of brackets, which is 5. And then plus 0. And we don't necessarily need these brackets written. We can drop them, since the brackets only contain a number. And for this second set of brackets, we have a plus outside. So we just drop the brackets and we have 5 plus 0, which is 5. Okay. B, we have g subtract f. So what I want to do is take negative 3, put it in g, take negative 3 and put it in f. I can write that this way. Alright. And now g of x, I go up here and follow the instructions. I can use brackets to separate these two outputs and put a subtraction symbol in between. We have x squared, and so we square negative 3, and then minus 2 times x, which is negative 3 in this case. So this completes g of negative 3. Now we'll compute f of negative 3, and f is 3x minus 1. So we would have 3 times the negative 3 minus 1 in the second brackets. Okay. The first set of brackets, this is negative 3 squared is a 9. Negative 2 times negative 3 is a plus 6. And we're subtracting, so I'll put my minus sign in between. Second set of brackets, I have a negative 9 minus 1. First set is 9 plus 6 is 15. I look outside the bracket and there's nothing there. Okay, no sign, no number. So I can simply drop these brackets and write a 15. And now we have minus, and then inside we have a minus 10, so I'll write minus 10 without the brackets. And this is 15 plus 10, and so in the end we get 25. G minus f of negative 3 is 25. Okay, I'll erase this just to make sure I have space for hg of 3. Okay, when we see two variables side by side, we interpret that as multiplication. In this case, we interpret that the same way, except first we insert 3 into each function notation. 3 inside of h, I'll put a dot between them, and then I'll write g of 3. Okay. Our first set of brackets, we're dealing with h, and so we have a square root of 3 in the place of this x, and then plus 1. I'll put a dot in between the brackets, and then I'll compute g of 3. G is x squared minus 2x, and so now we have 3 squared minus 2 times 3, close bracket. And we have in the first set of brackets 3 plus 1 is 4, so the square root of 4. 3 squared is 9. 2 times 3 is 6, and so we subtract 6 in the second bracket. And now we have square root of 4 is 2, and I'll just leave the brackets off. And 9 minus 6 is 3. 2 times 3 gives us 6. Okay. So, nothing really too new. We're still just simply plugging a number into a function and computing the output, except now we compute the output for two separate functions and then add, subtract, or multiply the two outputs together. Okay, the last one. We have f divided by g, and whatever that function is, what is the output whenever we use 1 as the input. We can take the 1 and put it into the two functions separately. We don't have to know what f divided by g is. Okay, f of 1 goes on top. We have a 3 times 1 minus 1. And then we have g again, and it is an x squared. So I write 1 squared and minus 2 times 1. 3 minus 1 on top would result in 2. 1 squared is 1, and then minus 2 times 1 is minus 2. So I end up with a 2 over a 1 minus 2. In the end, I get a negative 2. Okay, so what happens if we just simply insert a variable? Okay, we basically want to write out the algebraic expression for f of g and simplify, or f plus g. So again, now we insert x instead, so I just write f of x and then g of x. Okay, what is f of x? So reading f of x from example 1, we have 3x minus 1. And then we're adding g of x, so we don't have to worry about distributing a sign or a number. So I'll just write plus, and then I'll write g of x off to the right, x squared minus 2x. And at this point, we simply want to clean it up and combine like terms. X squared is my term with the highest degree, so I will move it over to the left. And then I have a 3x, which is the only x term in the expression. And now I'm only left with constants, negative 1 and negative 2. Combine those or add those, I get a negative 3. And so f plus g of x is x squared plus 3x minus 3. In b, we have a different variable. We have a g of z. That just simply means go through the expression and replace x with z. And so g of z will be z squared minus 2z, and f of z will be 3 times z, subtract 1. Oh, I don't need that parentheses there. What do you gotta do? Okay, I have parentheses around the z. Okay. And that's about the only, that's not the only way that we can write that, but we cannot simplify this expression any further. we just leave it like that. Okay, well, what is the domain of g of f? Well, first we will compute the domain of g. Okay, and if you'll look at g, I'll just simply write it below. G of x is x squared minus 2x. Okay, you don't see a radical, and you don't see a variable in the denominator of a fraction. Okay. And we also see whole number positive exponents for the variables. So the domain of g is from negative infinity to positive infinity. Well, what is the domain of f? Well, f of x is 3x minus 1. It's a linear function. Okay, and if you recall from section 1.3, linear functions of this form have a domain of negative infinity to positive infinity. And so we were told back on the previous page that the domain of g divided by f is the intersection of the two domains with the condition that whatever function we have on the bottom, which in this case is f of x, cannot equal 0. So this piece, the intersection of the domains of g and f, that actually just turns out to be negative infinity to positive infinity, since the two domains are identical, all real numbers. But we have a little bit of work here to do for f of x not equal 0, and so I just simply take f of x, which is 3x minus 1, and I do not want that to equal 0. Okay, I solved this. I don't know what I wrote 2 there for. I simply add 1 to both sides, and I divide by 3, and I'm just simply keeping the does not equal sign, and I end up with x does not equal 1/3. So if I do not want 3x minus 1 to equal 0, then at the same time I do not want x to be 1/3. So with this bit of information combined with all real numbers, I can change my interval notation and write d of g over f equals all real numbers from negative infinity up until we get to 1/3, and then we have to skip 1/3 and include everything past 1/3 out to positive infinity. So this is my domain that I was looking for in part C. Okay, we're using different functions for f and g now. Okay, we're no longer referring back to example 1. It says use the graphs of the functions f and g given below to estimate the output for f plus g, g minus f, and we're given particular inputs. So we'll write this as we did before. We'll simply write f of 3 plus g of 3. And so we sort of break this up into two problems. Alright, we cannot calculate f of 3. We have to look over here at the bottom graph, which is a graph of f of x, and we have to find x equals 3. So starting at the origin, I simply go to the right 1, 2, 3, and I track my way up to the line. Obviously f of x is a linear function, and this is x equals 3. So now that I've hit my line, I will break to the left towards the y-axis to figure out my output, and I see that I get y equals 2. So f of 3 is 2. Now for g of 3, I look at my graph of g of 3. Okay, I locate 3 on the x-axis, and I'm between 2 and 4. 3 is positive, so I track my way up to the parabola and then across to the y-axis, and I'm going to claim that my output for x equal 3 would simply be y equal 9. So in the place of g of 3, I write 9, and then I simply add the two outputs to get 11. F plus g of 3 equals 11. Okay, so we just simply have to read a graph in order to obtain our outputs. So b, we have g minus f, so I write g of negative 2 being our input for the two functions, and I write minus f, and I insert negative 2 in the f function notation. I will go over here and clean up my graphs because I'm going to have to read new inputs and outputs. G is up top. We have an input of negative 2, so I locate negative 2 on my x-axis. I track my way up to the curve and then across to the y-axis, and I read the coordinates of the y coordinate 1, 2, 3. I'm going to say g of negative 2 is 3.5. Okay, it could be 4. If I would have drawn my lines a little more accurate, I could have ended up with 4 there, but I'm just going to go with 3.5 now, and also the instructions did say estimate. So what about f of negative 2? F is graphed on the bottom, and now I start at the origin going over 2 units to the left, and there is x equal negative 2. I track my way straight up and then towards the y-axis, and this looks like I'll land, let's see, between 2 and 4. I have 1, 2, 3, 4, 5 units. I'm going to estimate and say I landed right between 2 and 4. I'm going to call that a 3. Okay, you may disagree. Maybe it's 3.5, maybe it's a little less than 3, maybe it's 2.7. I'm just going to go with 3, and so 3.5 minus 3 gives me the result of 1.5. Okay, C, we are multiplying the two functions. So I will compute f of 0, and whatever that turns out to be, I will multiply it by g of 0. Okay, these should be pretty easy to find. I just simply go to the y-axis. I am multiplying the y-intercepts of these two functions. Alright, g of x. Well, the y-intercept of g of x at x equals 0 is 0. So I could just go ahead and say that this product is 0. But just to be complete, I'll go find g or f of 0, and I go to my f graph and look at my y-intercept, and I see that y equals 2, and 2 times 0 gives me 0. And the last one, D, we have f of 1. F is on top. I insert 1 into f, place it on top, and then I insert 1 into g, and it will be my denominator. And now I compute these two outputs. F of 1, f is on the bottom. 5 is divided up into 5 tick marks. So here is x equal 1. If I trace my way up to x equal 1 and over, or to my f of x curve, and then to the right to the y-axis, let's see, 2 is divided up into 1, 2, 3, 4, 5 tick marks. So 2 divided by 5 is 0.4, and I have 4 of those units. So y equals 1.6. Okay, what about g of 1? Alright, 1 is positive, and here I have 2 on my x-axis. 1 would be right here in between 0 and 2. So I land there on my curve, and I track my way over to the y-axis, and to me that looks like 1, 2, 3, 4, 5. Looks like y equals 1. Okay, so apparently g of x must be, let's see, must be the function x squared. We don't need to know that. We've already read the y coordinate. We just simply go down here and replace g of 1 with 1, and we compute 1.6. For f divided by g of 1, we get 1.6. Okay, so beside simply adding, subtracting, multiplying, and dividing two functions, there's also an operation called composition of functions, where we simply take the algebraic expression for one function and place it inside of the other. Okay, here's the notation for the composition of f and g. Okay, and it's represented by this open dot. Okay, please note that f solid dot g is not equal to f with an open dot g. This open dot is reserved for the composition of the two functions. This dot symbolizes multiplication. So multiplication does not the same as the composition. Okay, this is a little more explanatory as to what we actually do to compute the composition. We simply take g of x and put it inside of f. Or you could look at it as X goes into G, and then that output goes into F. Okay. We'll read this note here. It says the domain of f of g is the set of all values x in the domain of g such that g of x, the output, is in the domain of f. Okay. More precisely, x is in the domain of g. Okay, if we're computing the composite of f and g. Okay, g goes inside of f. So first we want x to be at least in the domain of g. And then whatever output we get from that must be in the domain of f. Okay. This more than likely doesn't make it clear as to what we actually do to compute this new domain. So down below we will work some examples. Okay, and for right now, we're not going to worry about the domain. We're just simply going to work with composition of functions and see how this plays out when we have a particular input and we want to put that inside the composition of f and g. So we'll just simply write down what we saw above. F, okay, it's on the outside, and here I've written f on the outside, and g is on the inside. So I put g inside f, and then 2 first is input into g. Okay. So one way to look at this is that step 1 is to compute g of 2. Okay, what does that give us? Well, g of x is x squared minus 5. So I write 2 squared minus 5, which is 4 minus 5, and I get a negative 1. Now, we take this result and we go back over here, and we can rewrite our expression. So instead of writing g of 2 inside, we can now write negative 1. So what is f of negative 1? Well, we pull down our expression for f. We have negative 3 times x. We replace x with negative 1, and then we add 2 to the right. Negative 3 times negative 1 is 3. Add 2, we get 5. And so this is the end of the road. Okay, 5. Alright, now we've swapped the order of g and f. Okay, so g is going to go on the outside this time. We're going to first put negative 3 into f and compute that output. So what is f of negative 3? Okay, same expression that we used for a. We have negative 3, replace the x with the negative 3, and then we add 2. Okay, negative 3 times negative 3 is a positive 9. 9 plus 2 is 11. We take 11. We go back to the expression that we wrote for the composition of the two functions. We replace f of negative 3 with 11. And now we compute g of 11. The function g is x squared minus 5. So instead I write 11 squared minus 5. 11 squared is 121. If I subtract 5, I get the result of 116. Okay, so I can go back over here and just simply write g of f of negative 3 equals 116. And likewise for a, f of g of 2 equals 5. If you wanted to write this with an arrow diagram, we could say this from here to there, and I'm doing B here. I'll write it below G of F of -3. Okay, what we've done is we computed F first, and we input -3. F mapped -3 to 11, and then we used 11 as the input. We mapped 11 to 116 using G. And so, in other words, G of F takes -3 and maps it over to 116. Okay, our last example, we have the composition of two identical functions, f composition f. So I simply use the same function over, but not the same output. Okay, this is an alternate way to write it. F of 4 inside of f once again. So I'll go down here and I will first compute f of 4. F is -3 times x, so I write -3 times 4 instead, and I add 2. -3 times 4 is -12. If I add 2, I will get a -10. Okay, so we take -10, and we replace this f of 4 entirely with a -10. And so now we pull our same expression up here, and instead we multiply -3 by -10 and then add 2. And so we get a positive 30 plus 2, and we get 32. Okay, so I can write for my input 4, if I'm going to write an arrow diagram, and then on the very last end I would have 32. And what maps 4 to 32? Well, it is f of, or the composition of f and f. Okay, example 5. We have some new functions, f, g, and h, and we simply want to find the expressions for f of g and g of f. So f is on the outside, it's the farthest away from the x. So I'll write f notation first, and now I will input inside of f g of x. Well, what is g of x? Well, we can just read it from the top as the square root of 2x plus 1. Okay, and this notation is simply telling us to take f and replace all of the x's inside that expression, specifically this one. Replace the x's here with the square root of 2x plus 1. And so I have a -3 parentheses plus 2. This is where the x was, and now I just simply put this radical in its place. And with this expression, it's already in simplest form. There's not really anything else we can do to it. and we weren't inserting a number, we were just simply inserting a variable inside of that. So this would be the end of A. Okay, so now we've swapped the order. We now want to put F inside of G, and we want to use a different variable, T. So we calculate F of T. We just simply take the function, the expression up above, and replace X with T, and then whatever we get from that, we place it inside of G. Alright. That would look like this. F is negative 3x plus 2, so instead we write negative 3t plus 2. The function g is a radical. Inside the radical we have 2, and then we have x, so 2 times x, and we don't want to write the x. We're going to replace the x with negative 3t plus 2 instead. And then to complete g inside the radical, we have a plus 1. And we can clean this up a bit. We can write negative 2 times negative 3, or I'm sorry, just 2 times negative 3. We can simply distribute this 2 inside the parentheses. We will get a negative 6t, a plus 4, 2 times 2, and then a plus 1. And at this point it should be obvious that we can keep the negative 6t and add the 4 and 1 to reduce our expression to its simplest form. Okay, so this expression represents the composition of G and F of T. Now C, probably the most difficult question of this section. Okay, we want to know not the composition of the two functions. We've already calculated the composition of F and G. It's up here at the top. But now we want to talk about what is the domain of that. So I'll simply just write the composition here. Without the parentheses. Okay. And our first step is to figure out what are the domains of F and G. Okay. The domain of F being a linear function, would be all real numbers. The domain of G would be different. Okay, G contains a radical. So for G itself, we would write 2x plus 1 is greater than or equal to 0 to express the domain. Well, we can do a little bit of work to this and find out specifically what x is related to, solve the inequality, and I don't want to write a plus. So we want this expression to be greater than or equal to 0. I write minus 1. I get a 2x greater than or equal to negative 1, and then I divide by 2. And I get x is greater than or equal to negative 1/2. So now that we've found the domain of F and G, how do we interpret these two domains to figure out the domain of the composition? Okay, One way that could be expressed is with this notation. Okay, we definitely want x to be in the domain of G, but it's not that simple. We now want those values to be combined through the intersection with this set of values. Okay, we want the inputs x such that g of x, when we put x inside g, we'll get g of x instead. We want g of x such that it is in the domain of f. Okay, this, in a general way, is the domain that we're looking for. Okay, well, I'll go back and I'll replace d of g with the interval notation of this set of numbers, and that just simply gives us from negative 1/2 to infinity. Now, the way this domain was set up is so that g of x would be a real number. This domain was based off of the fact that we want the radicand 2x plus 1 to be positive. If it's negative, then we get the square root of a negative number, which is not real. Okay, so as long as we use this domain for g, g of x will be a real number. Now, what about d, the domain of f? Well, I can replace that with all real numbers. So by design, g of x is a real number. And so what we get is basically the domain d f composition g is equal to 1/2 to infinity. Okay, so we have established that the domain of f equals negative infinity, positive infinity, and we've also established that the domain of g is from negative 1/2 to infinity. Now, I can write out an expression, a set of instructions, in order to figure out the domain of the composition of g and f. That would simply be the domain of f. We want the input to be initially in the domain, the first function that the input actually goes into. So if it's not in this first initial function, then it can't be in the domain of the composition. Then, whatever we get out of that first function f, we want the f of x, in this case, that's our initial function, we want the output of that first function to also be in the domain of g. If it's not in the domain of g, then we won't get an output in the end, no matter if we have an actual real number f of x. Okay, this tells us what we want to compute. This we can write in a different way. Okay, what is f of x? Well, it's negative 3x plus 2. Well, what is the domain of G. Well, we want whatever this is to be inside of x greater than or equal to negative 1/2. Okay, what you have to realize is that this f of x is going to take the place of this x. F of x is the input, and that's what this x represents. And so we take that and we write minus 3x plus 2 is greater than or equal to minus 1/2. Okay, if we solve this inequality, we get the result that x must be less than or equal to 5/6. Okay, and as you're solving this inequality, don't forget to switch the direction of your inequality because of this -3. Okay, so now we have both pieces of our domain of our composition. We write the domain of f, which is all real numbers, intersection the domain of x such that f of x is in the domain of g, and that gave us this inequality. And so we have x is less than 5/6, so from negative infinity to 5/6 with a bracket. This is the only restrictive interval. Okay, for domain of f, it can be any real number, and so in the end, we just end up for the intersection with this second part, negative infinity to 5/6. This is the domain that we were actually looking for, and we can confirm that with a TI calculator. Okay, little trick to entering in a composition function. So try to pay attention. I already have the functions entered. Okay, in this case, I'll clear this and just start from the beginning. Okay, alright. Perhaps you turn on your calculator and you're at the home screen. You want to graph something, then you go to the Y editor. Okay, in the Y1 line, we want to put our input function, the first function, which is f in this case. Okay, the function closest to the x. Okay, and when I say closest to the x, if we were to actually solve for the composition of g of f, okay, we would insert x into f and then f of x inside of g. So f is closest to f of x. F is going inside of g, and so we're going to put f first, and it is a minus 3x plus 2. And now we're not simply going to put g of x in y2. We're going to do something a bit different. You probably haven't seen this before in any of our algebra classes. Okay, I was trying to hit the square root symbol there. Okay, g is square root, and it has a 2, but we're not going to multiply 2 times x. Instead, I'm going to hit the variable key, and I'm going to use the function that I inserted in y1. And so you see it enters y1, so 2 times y1, and then we have a plus 1. Enter. I don't want to see f of x on our function. I'm only interested in this composite. So I'll simply highlight the equal sign for y1 and hit enter, and then it'll no longer be shaded. So I've turned off y1, and now when I graph, I'll only see y2, and there it is. Okay, you can see in reference to the domain, we come in from negative infinity and we approach 5, 6, almost 1. Another way that we can sort of verify this is to go to the table. Okay, and here in the table we see x and y2. y2 is our composition function, and we're good to go with the negative inputs in the x column. Let's travel down through here and look at the positives. Well, for all of the positives, 1 included and beyond, we get an error, and that's because those values are not in the domain. If I go back to my graph and I hit trace, and then I type in a 5 divided by 6 for x and hit enter, you will see that I actually have a return value. But if I type in anything greater than 5, 6, let's say I type in a 0.84, so I'll hit trace again and I'll enter a 0.84, enter. We have no y output. That's because 0.84 is beyond 5, 6. It's not in the domain. Okay, so our last example of this section, example 5, we're going to use the graphs instead to compute the composition outputs. Okay, so in this case we have f on the outside and 2 goes into the g, so g of 2 is inside of f. Well, what is g of 2? We look to our g of x graph and we locate x equal 2. Okay, and we sort of theorized earlier that g of x is x squared, and so one would expect to get 4 as an output. Okay, we went to x equal 2 and we traced our way back to y equals 4, right there. Alright, so in other words, we're going to take this 4 and put it inside of f now, and then we'll have to use the graph of f down here below to find the output. First we locate x equal 4, we make our way up to the line, because f of x is a linear function, and we trace our way over to the y-axis, and we see that we hit y equals 1, and so f of 4 is 1. So the composition f of g of 2 is 1. F of g of 2 equals 1. Okay. We're going to have new input and output values for this next example. And now we're inserting a different number and the functions have changed order, and we are putting in f inside of g. So the first question is, what is f of negative 5? We look to f and we count 1, 2, 3, 4, 5 on the x-axis to the left of the origin, x equals negative 5. We trace our way vertically till we hit f of x, and then we work our way to the right until we hit the y-axis, and it looks like we hit y equals 4 exactly. And I am just going to go with y equals 4. It said estimate anyway, so 4 is good enough. This is input into the g function. And now we go to g and we locate 4, and like I said before, we suspect that this is x squared. And if we trace our way over to the y-axis, it does look like we hit 4 squared, 16. And so 16 is our final stop, much like 1 was above. One last example to work, and we'll be done with this section. Oh, I just erased everything, but that's okay. G of f of 0. So G goes on the outside again, and f of 0 goes inside. We compute f of 0 separately. If we look to the right at our function f and we trace our way up along the y-axis, we hit y equals 2. So this gets inserted inside of G, and now we calculate G of 2. We locate G, the top with an x equal 2, and if we square 2 we would expect to get 4, and that's exactly where it falls. So composition of G of f of 0 equals 4.